I hope, thank you for waking up so early. I hope I'm making it worthwhile. So the organizer of this conference has asked me to say a few words about quenching, or the quenching mechanism to produce a quiescent galaxy like this one. So let me start with considering the large range of quenching mechanism. And obviously galaxies are not highly universes, and they interact with their environment, and so one has to consider the entire baryon cycle and the entire galaxy ecosystem. And this is one image that sort of illustrates this point from Simon Levy's paper. So traditionally, these mechanisms have been divided into roughly two internal processes and external processes. And so in the simplest case, we do have a highly universe, and the galaxy is completely isolated. This is a closed box model using the nomenclature of Veilleux late 1980. So basically, the gas is simply exhausted. It's consumed into stars. And the galaxy runs out of gas, and this is what is called traditionally starvation, or more graphically, recently, strangulation. But star formation and also accretion onto supermassive black holes inject energy, inject momentum, radiate, and influence the gas, the surrounding gas, and can actually launch galactic winds. And so one has stellar processes and AGN processes. And one question, so the launch outflows, one question is whether the outflow just is really ejecting material completely outside the galaxy and doesn't come back. So you really quench the star formation. Or whether the material is just deposited into the halo and just prevents star formation for us via heating the halo. So that's an open issue. We'll come back to that. So this is for internal processes. And then, of course, there's the exterior, the external processes. And so gas may be accreting onto the galaxy, onto the halo of the galaxy, or onto the galaxy itself. That's shown in blue here in this diagram. So in the simplest case, you have an accreting box model, and you have competition between star formation rate, gas inflow, and also gas outflow. In the more massive system, where the halo mass may be a few times 10 to the 12 solar masses. In that case, the accreting gas reaches sound speed and shocks and heats up. And this can actually prevent also star formation. This is so-called halo quenching. And once you have hot gas either around the galaxy or between galaxies in a cluster, then you encounter the effect of course, of ground pressure stripping, even evaporation for smaller objects. And in a cluster environment, galaxies are social beasts. They like to live together. And so they will interact with each other in a tidal stripping if the encounter is at low velocity in groups or in the field. And you can have a harassment where in a cluster where the velocity of the encounter is large. So in the following discussion, I want us to keep in mind this whole range of processes, and the complexity could be that there are quite a few of these processes taking place at the same time, competing with each other. So what I will do, the plan for today, is play a little bit like Hercule Poirot and Sherlock Holmes detective. I'll have a crime scene at z=0. I'll go over that very briefly because we've already had quite a bit of discussion of the redshift 0 universe. And most of my discussion is really about evolution with cosmic time all the way to redshift 3 or so. And then I'll emphasize the quenching mechanism for the high mass system, just in the interest of time. Larger than, stellar mass larger than 10 to the 11 or so. So the z=0 scene, the prime scene, this has been shown before, so I won't spend too much time, but the point to emphasize is that all numerical simulation that includes quenching must agree with the observation at redshift 0. The bimodality of galaxies, a very well-known bimodality of galaxies, going all the way to Hubble 1924. This is, I promise, this is my oldest reference here in the talk. So bimodality in morphology, bimodality in colors, bimodality also in star formation rate versus stellar mass, so-called main sequence of star forming galaxies. The numerical estimation also have to explain quiescent galaxies, and we had a very nice discussion yesterday about that as well at redshift 0. The fact that they're made out of old stars, roughly 10 gigayears or so, with slow decline. This is luminosity weighted slow decline with radius. And the point that is particularly relevant for quenching is the fact that alpha elements are supersolar compared with iron, factor 2, factor 3. We heard about factor 3 in the previous one of the talks yesterday. But this seems to indicate, at least the simplest explanation for this supersolar ratio is that star formation history is truncated on the time scale of less than 80 years. This was a paper by Green et al. That goes all the way to RE of 2.5, which is very nice. So I'm sure we'll hear more about that today or in the coming days as well. Now, one thing that was not mentioned is the star formation efficiency. One has to remember that star formation is actually not very efficient, less than 10% if we consider the fraction of baryons in the form of stars. And that dependence, that ratio depends on stellar mass being smaller at low mass, as shown in this diagram by Kratzoff. At low mass, which has traditionally been, stellar processes have been invoked to explain this low ratio, but at high mass as well. And there's just not enough, most likely not enough energy in the star from stellar processes to do this. And so one invoked AGN. Most of the numerical estimation invoked AGN feedback, but there's also halo quenching that could be also happening at the highest halo mass, stellar mass. So one thing to remember now, where are the baryons? If they're not in stars, many of the baryons are actually around the galaxy, and that's not been discussed so far, although I'm sure that will be discussed further in this conference. But at low redshift, these circumgalactic environment are very rich in metals, in dust, in cool gas. They're ubiquitous, large, extending to 100 kiloparsecs. That's from observation from absorption line study, from the ground, and also with HST. But also there's now new direct observation with imaging. The dust, the X-ray gas, etc., etc. Lyman alpha also at higher redshift. But the point is that there's a lot of metals in these supergalactic medium. May contain more metals and dust than the galaxies themselves. So they really cannot be neglected in this when considering the entire galaxy ecosystem. They're most likely the cumulative effect of enrichment by alpha. Now, so this is set up to CNet equals 0. Now let's move on to high redshift, 0 to 3. This version of this image, this plot has been shown yesterday as well. The fact that star formation rate density is an order of magnitude larger at redshift 1 to 3, of order 6, 7 to 10 or 11 gigayears. It's very well known. And this corresponding stellar density increases a function of redshift. Now, one thing that has not been mentioned yet is the fact that the AGN accretion rate history also matches quite nicely the star formation history. That's shown, the black curve is the star formation history, and then the other curves are various rendition of the AGN accretion rate density as a function of redshift. So this is actually a very nice match. So whenever you have star formation, you do have an AGN also, to first order. Now, the increase of star formation rate density as a function of redshift also translated into the main sequence moving up as a function of redshift, about an order of magnitude or so. Or at a given mass, at high mass, there's an order of magnitude increase. One thing that has not been mentioned yet is the fact also that the molecular gas fraction also increases as you go to higher redshift, quite steeply, 1 plus e to the third power. And that's a driving factor, most likely, of star formation rate evolution as well. So it's of order 50% at redshift 2-ish. Perhaps more relevant to this discussion of quenching is the diffraction of stellar mass in the quiescent galaxies. This is shown in this nice plot by Musen. So it rises up to about matching that of the stars in the star-forming galaxies. And that happens, this is another version of the ratio here. And so at 50%, it happens at about redshift of 0.7 to 0.8, so about 60 years ago. Now, one thing that is not shown in this plot is the fact that the majority of quiescent galaxies are in compact systems. Compact systems that have radii about 5 times smaller and density about 100 times larger than quiescent galaxy of the same number density at redshift 0. So it's a very big difference. And so that's shown in this plot here by Van Dorken, where the fraction of the number density of quiescent compact galaxy is pretty close to the total number density of quiescent galaxies. So they really are the majority of quiescent galaxies, at redshift 2 or so. Another thing that is shown here is the fact that this fraction of quiescent galaxies does not depend only on redshift, but also on compactness. You know, basically the stellar velocity dispersion, the equivalent of the stellar velocity dispersion, or the stellar density, surface density, or number density. In that fraction, it's really a very sensitive function of the compactness. This is the compactness, and it really dominates that by compactness. So something happens to these galaxies at redshift above 2, probably above 3, that makes them compact. So this process is being called compaction, where the formation of compact galaxies, definitely through dissipational process, to get these very high density, perhaps gaseous merger, violent disk instability, and there's a few other possible processes. But there's certainly highly dissipational to produce these density system, compact system. Now, why do I mention this? Is there seems to be a correlation between compaction and quenching. And galaxies that are compact very quickly thereafter, or perhaps immediately, are quenched. This is shown in this plot, a very recent paper by Veilleux, where they actually argue that compaction happens a bit before quenching, in the sense that this is the star formation rate with respect to the main sequence. So these objects are in the main sequence, and these are below the main sequence. And this is 1 kiloparsec stellar surface density, so the very central part of these objects. And the point that they're making, and there are objects here that are on the main sequence, but are already very compact. So they went through compaction, but they're still forming stars. But there, just immediately thereafter, they do quench, and they fall down into this region, which would be a quiescent core, the so-called red nuggets. So those red nuggets are the core of galaxies that we see today, and the standard picture is that they grow their stellar envelopes via dry mergers. So the point I wanted to make, and I'm sure that's going to be discussed also in this conference, is the fact that about 50% of the material of the stars form at redshift larger than 0, larger than 2, via this compaction process. And there's a bit of residual star formation after redshift, less than redshift 2. And then the rest is through dry merger, the other roughly 40 or 50%. So I emphasize compaction quite a bit because it really is directly related to this quenching mechanism. So let's discuss quenching mechanism for a high mass system. Again, 10 to the 11 or so and above galaxies. And there's a lot of hints that this quenching for these systems is fast. That was, I already mentioned the elevated alpha to iron ratios at redshift 0, but now there's new observations that also indicate that this ratio is elevated even at redshift 2. So just recently quenched galaxies at these redshifts, so the so-called red nuggets again. That's shown in this plot by the red, but it really follows basically the same place as z equals 0 quiescent galaxies. There's also observation of a few galaxies that are undergoing quenching, And they have a post-starburst spectrum with rapidly declining H-alpha emission, so rapidly declining star formation rate, but a strong H delta, which indicates ages of less than a gigabit or so. Again, this indicates the compression is fast. It also, there's new observation, again, pretty recently, that shows that not only is it fast, but it also seems to be inside out. And that points to internal processes rather than external processes. So this is one of the plots from this paper by Takeli, where the specific star formation rate as a function of radius stacked over several galaxies is either rising or flat, but many of them are rising to higher radius, which is indicate a picture of where the quenching takes place in the middle first and then propagates to the side. So again, this is an indication that gives us some hints as to what sort of mechanism probably for quenching the star formation is ongoing in the system. Now, these compact cores are really ideal conditions for negative feedback. You have all the perfect ingredients. This is like a perfect storm where you have high surface density of gas, also stars, which produce high density of star formation, but it's also ideal condition for accretion rate, high accretion rate onto the supermassive black hole in the system. So both the stellar processes and AGN accretion injects energy, momentum, radiation into the surrounding medium and ideal condition to launch winds. So for instance, the critical parameter for starburst, in the case of energy conserving winds, no radiation loss, and sort of simple picture, pressure that is produced by an energy injection into the surrounding medium goes as the surface density of star formation, basically. Star formation rate divided by the injection zone, the radius of the injection zone. So in the local universe, when this number is larger than 0.1 or so, we see winds. Winds are probably launched even at lower values than that, but above 0.1 in those units, we see winds all the time. It's the same thing for quasars. Now, one thing that I really want to emphasize is the fact that quasars are like a ticking bomb, in the sense that they have potentially a very lethal effect on the galaxies. Just the radiation produced by accretion onto the supermassive black hole for a black hole mass of 10 to the 8 solar masses corresponds to 10 to the 60 ergs, which is basically basically the total energy of the galaxy and the gravitational energy of the galaxy. And so, in a sense, to me, it's surprising there are galaxies around the supermassive black hole, because it would be very easy to just push it off. But they do exist, and so there's really a fine-tuning. So the question of how much of the energy that is produced by the quasar is captured by the ISM, is tapped by the ISM. So potentially lethal to a galaxy. Now there's circumstantial evidence that AGN plays a role in galaxy star formation. So this is the fact that quasar hosts have a tendency to be located below the star formation main sequence. This is seen at redshift 0. These are the blue and red points. Same thing here. Secret 2 galaxies well below the main sequence, but also even at intermediate redshift, work by Matsuoka, and also perhaps extending to even higher redshift, although the number statistics is clearly much more difficult there. So there's circumstantial evidence that they may be playing a role. Going back to the compact star-forming galaxies, more than 50% of these objects do host a luminous AGN. So the AGN is already there and could make some work and do some damage to these star-forming galaxies. This number is definitely a lower limit in the sense that there are objects, as in this case here, the quenching galaxy that I mentioned earlier, where it's not detected in the X-ray, but it's detected from optical spectroscopy. So there's at least 50% of these compact star-forming galaxies that do host AGN. Now, whether or not they play see now there's stronger and stronger evidence that do play a role in driving winds in these objects. This is work by Christian Schreiber and Jensel's group, and then we'll hear more about that also from the coming talks as well. So there's strong evidence for spatially resolved, ionized starburst and Aegean winds in the most massive star-forming galaxy. And that's shown in these plots. It really picks up at stellar mass above 10 to the 11 again. That's why I use that number in my talk. But the mass alpha rates can be very large, and the so-called mass loading factor, the mass alpha rate divided by star formation rate, can be very large as well. Of order unity or 3 is fine for a starburst movement, but having a ratio of 10 becomes quite uncomfortable and seems to indicate Nietzschean driving. Now this is only the ionized portion of the wind, and so there are lower limits to these numbers. And one thing that we've learned at low redshift is the fact that cool gas often is the energetically dominant gas phase of galactic winds in gas-rich or gas-rich equation. Mark 231 is sort of the prototype of that, where we see molecular outflows and neutral gas outflow. On the left is the neutral gas outflow from sodium, or H1, extending to 2 to 3 kiloparsecs. On the right is the molecular gas, either from Herschel, OH molecule, or a CO with ERAM, and just limiter wave interferometer. So the lessons that we learned from the low redshift in the nearby ULARCs, and remember nearby ULARCs are mergers, so they're sort of undergoing their own compaction event at low redshift. Not quite as spectacular at the highest redshift, but quite similar. What we find that 70% of local ULARCs have molecular winds, and they're wide-angle winds, so they can actually cause quite a bit of damage to the galaxy. These are not jets, these are wide-angle winds. These are the typical velocity for the molecular gas, all the way to maximum velocity of essentially 1,000 kilometers per second. Again, very large compared to the escape velocity. The kinematic trends, we see kinematic trends with Aegean luminosity that suggest that we're seeing quasar mode feedback in the most luminous object, where quasar-like luminosity. The dynamics are shown here. The size for the molecular gas is up to a few kiloparsecs. These are lower limits, basically sensitivity limit. When we look at the neutral gas, the sodium, the size extends to up to about 10 kiloparsecs. The numbers are similar whether or not we're looking at the neutral gas and molecular gas. We're getting mass outflow rates of several hundred solar masses per year in these local ULARCs. So these are the coal gas is the energetically dominant phase of these outflows. So the numbers that I discussed before at high redshift are lower limits, and one really should, in the very near future, look for the neutral gas or the coal gas. This is sort of the trends that we see local ULARCs. Velocity of outflow, either 50% or 84% velocity, percentile velocity, increasing to larger Aegean luminosity. This is work by Stone, student in Maryland, and this is work by Ciccone, where the mass alpha rate versus LHEM really picks up when the Aegean luminosity is large enough to really drive these alpha. And these are just starbursts. So there's really a two-dimensional parameter space where you have LHEM and star formation rate, and the alpha can be driven by either one of them depending on which one is the dominant one. One thing I want to mention also is the fact that one really has to remember the circumgalactic medium. Now at redshift 2 to 3, find that this is work by Krushaska and collaborators, there's a very large amount of cool alpha enhanced gas in the halos of massive quasar hosts. Basically as much gas in the halo that in the galaxy themselves. This is from carbon 2. And so the color basically indicates the amount of material, the column density in these halo. This is the scale is 400 kiloparsecs or so. And so one thing that the next paper in that series by Lau et al. Also showed that the velocities are very large. The velocities of the carbon 2 and carbon 4 are very large at 90 percentile. so in that paper, they argued that the broadline profiles indicates non-gravitational motion indicative of electric winds, either ongoing winds or just residual winds, where the source is not there anymore. Another indication of winds, even at a redshift up to 6, using millimeter wave difframetry, is the detection of raw carbon-2 on scale again of 20, 30 kiloparsecs in radius distance from the reservoir itself. So there's some evidence, perhaps, that winds can play a role even on that sort of large scale. In that case, they may actually be quenching rather than just preventive winds. Now, just very briefly, I'll just spend just a few minutes. At low mass, there's already been quite a bit of discussion of that. There's a nice paper by Peng and collaborators that discussed this, looking at the Sloan Digital Sky Survey and arguing that if you use the stellar metallicity of the star-forming system versus the quench system, one can actually derive whether or not strangulation or quenching winds is at play. So they compare the stellar metallicity of the passive system, which is compare that with the star-forming system. Look at the difference between the two, and that's plotted here. This is basically the difference in stellar metallicity versus stellar mass. And they argued that this difference is easier to explain via basically a closed box model of strangulation rather than quenching winds. There's no constraints on the actual how the strangulation is done. It could actually be due to preventive winds. But using a closed box model, they find that the best fit, and that's shown in the green here, is strangulation time scale of 4 gigayears for these objects, all stellar mass, up to 10 to the 11. So again, these are for the lower stellar mass system. So it's a bit different story than for the high mass system. They also argue that just comparing the ages derived from the stars again, from the stellar spectra, from Sloan again, there's a difference, systematic difference between the passive system and the star-forming system. That difference is essentially constant, of order 4 gigayears for all stellar masses that in their sample up to 10 to 11. Okay, so let me just summarize. I think I'm out of time. For the high mass system, which was the main focus of this discussion, larger than 10 to the 11 or so, quenching is fast and inside out, less than a gigayear time scale. It's often associated, or perhaps even preceded, by compaction. This compact galaxy is really ideal for feedback, either stellar feedback and AGN feedback. I'm actually agnostic about the actual feedback here. But we do see powerful AGN feedback in a large fraction of compact system, both locally and distant system. The main question is whether or not they really have an influence on large scale, and are they able to quench star formation? What we're seeing, perhaps evidence at high redshift in the CGM, that the CGM is turbulent with velocities that are very large that suggest that it's not just gravitational, there might be a wind effect here. But perhaps at the highest mass, you need a more global processes. And that's, I think, where halo quenching may actually be taking place, where the masses are quite a bit larger than 10 to the 11, 10 to the 12, of course, in stellar mass. We're talking about different type of elliptical galaxy, more boxy elliptical galaxy, where gas doesn't seem to be playing a role in their formation. At the low mass end, the picture seems to be different, and then I just brought up one paper, so I'm sure there'll be a discussion about that throughout the conference. But strangulation seems to be favored versus quenching winds, and where the time scale is different also. Instead of less than a gigayear, it seems to be pointing to time scale of several gigayear, 4 gigayears, independent of stellar mass, up to 10 to the 11. Thank you.
I'm Vladimir Villaris. Thank you for your very nice review. My question is about the compactation process. what is the driver of this process? I guess that is related to a dissipative merger, which is transforming also the morphology. So, what's your comment about your opinion about this process? What is producing the compactation that is going?
There's actually a whole slew of processes that can do it. The question is which one does it? I think it will depend on redshift. So, for instance, at redshift 3 or so, when galaxies are already there, then gas-rich merger could do it. It doesn't have to be major merger. Minor merger can also help. One thing that I didn't mention is that those compact galaxies, both star-forming and quiescent, have a component of rotation. And their Sorsic index of 2 or 3 of them, sometimes at 2 or 3 at these higher redshifts. So they have this, they do have a rotation component. So minor and major merger would do it. If you go to higher redshift, I should say also that you could also have the disk become unstable, highly unstable. We see those clumps in those galaxies. And they're star-forming clumps. And so they're highly unstable to star formation and just clump interaction. Now these clumps can eventually merge and basically form a bulge through this process of compaction. And then the other process that I didn't mention here is just that cold stream. At higher redshift, the cold streams comes in and they collide with each other and in the middle, and you can get compaction, a huge amount of dissipation, and you produce compact galaxies. So there are many processes. It probably depends on high redshift, but really, in terms of observational constraint, I would argue there's not enough now to really discriminate between all of these processes. But that will come.
Yes. So you say that we need a lot of quenching at high redshift with massive galaxies. It cannot be strangulation because strangulation is a very long time scale for behavior. So is it maybe related to the very high black hole masses at high redshift that people have found? So you could have more HEM feedback at high redshift because of that, and also because of the thick disk, it can be disk and very turbulent disk.
Yeah, I think that's quite a reasonable possibilities. I want to be careful when I talk about compaction and HEM feedback and all that. I really think, in my opinion, and that's a biased opinion, is that it works perhaps at 10 to 11 and larger, but not at the very extreme end. So depending on the exact black hole mass we're talking about, in the case of the CD galaxies, the huge, massive elliptical galaxies, they do have high black hole mass, but I'm not quite sure compaction works in these extreme systems. I think they're diffuse, they're boxy, as you well know, they're boxy, and there's less evidence of compaction where you do have dissipational processes going in the center.
Yes, one more very brief. Sorry, Alison. So you talk about compaction as if it's this very active process, so something that acts to compactify the galaxy and then its quenching occurs. But really these metrics of compact stellar mass, these are just metrics of the bulge fraction of a galaxy. So are we maybe just seeing quenching that is associated with the mass of the bulge, which is then in turn related to the presence of the black hole, and it comes back to an HEM feedback?
Yeah, no, I think you're quite right. I think this connection, as I tried to emphasize, the fact that this is an ideal system for feedback. You have the high stellar mass density, gas fraction is high, the high star formation rate density, and you have a black hole that is proportionally large. And so all of these can work in the direction of feedback and helping in quenching. So I think that picture is very consistent with what you were saying.
Okay, we have to move on, so thank our speaker again.